Every day, billions of clicks flow through URL shorteners. When you click a shortened link, your request joins a digital torrent, funneling a massive volume of global traffic through a highly constrained bottleneck. This chart illustrates the core problem: scale asymmetry. On the left, the write path generates about 10 million links daily. On the right, the read path resolves those links, generating over 1 billion requests a day, a 100-to-1 read-to-write ratio. When a user creates a link, they might tolerate a second of loading time. But when they click a link, the redirect must execute in under 10 milliseconds. Anything slower feels broken. This creates two different operational realities. The write path has a generous latency budget, while the read path has a zero-tolerance budget. If you build a symmetric web architecture, where link creation and redirection share the same monolithic servers and databases, the sheer volume of read requests will instantly crush the system. To survive this pressure, the system requires strict architectural boundaries. We must decouple the write path, the read path, and the analytics pipeline into completely isolated architectures. The first challenge is the write path, converting a massive, unpredictable long URL into a unique 7-character alphanumeric key. This flowchart shows the most common junior-level mistake. It takes the long URL, runs it through an MD5 hash to get a 32-character string, and slices it down to just 7 characters. This creates a mathematical trap called the birthday paradox. Because we reduce the entropy pools so severely, a second, different URL can hash down to the exact same 7 characters. This collision overwrites the data and breaks the link. To eliminate collisions, the system must abandon hashing. Instead, we use a centralized distributed counter service, built on Zookeeper or Redis, to assign a strictly increasing unique integer to every new link. This sequence diagram maps the correct approach. The API server requests an ID from the Redis counter. It receives a base 10 integer, like 123456789. It passes that integer through a Base62 encoder, resulting in a compact alphanumeric string, like 15FTGG. Base62 uses all lowercase and uppercase letters, plus the digits 0 through 9. With a 7-character length, this format provides 62 to the 7th power, roughly 3.5 trillion possible combinations. Shifting from probabilistic hashing to deterministic counting guarantees 100% collision-proof ID generation while remaining highly compact. Once generated, we store the shortcode as the primary key in a NoSQL data store, like DynamoDB or Cassandra, mapped to the long URL. Now we face the fundamental choice of the read path, the HTTP 301 permanent redirect versus the 302 temporary redirect. As shown in this split screen, a 301 redirect optimizes infrastructure by telling the browser to cache the destination locally. On the second click, the request loops back directly from the browser cache, completely bypassing the server. But for this product, that efficiency is a fatal flaw. If the browser bypasses the server on repeat visits, click analytics become invisible, and the link destination can never be updated or deleted. On the right side, the 302 redirect forces the browser to query the server on every single click. Every request travels to the server block, generating a tiny analytics packet before returning the destination. This visibility is why the 302 redirect is the standard for URL shorteners.
It guarantees data accuracy and lifecycle control. The trade-off is clear. The 302 redirect tracks every click, but forces the read architecture to absorb 100% of the world's traffic without buckling. Relying solely on a NoSQL database for billions of 302 redirects will cause latency to spike and read costs to become prohibitive. This vertical 3-tier architecture solves that. User requests flow in from the top, hitting an edge CDN first to catch highly requested regional links. 80% of requests bounce back from the CDN. 15% miss the edge but hit the regional Redis cache. Only 5% penetrate all the way down to the NoSQL database. This works until a new, uncached link suddenly goes viral. This creates a specific infrastructure failure known as the thundering herd. Thousands of concurrent requests for that viral link will simultaneously miss the empty cache and bombard the primary database, causing a cascading failure. We solve this using a pattern called request coalescing, or single flight. When the server detects a stampede, it pauses the herd. It allows only one request to query the database, populates the cache, and then serves the result to all waiting requests simultaneously. In this architecture, caching functions as a mandatory defensive shield for the data layer, insulating the persistent store from the extreme volatility of internet traffic. Every 302 redirect generates critical data: the timestamp, the IP hash, and the referrer. A common architectural anti-pattern is attempting to write this click data to a database before sending the HTTP redirect back to the user. Any database slowdown during that synchronous write will push the redirect latency past the 10 millisecond budget, immediately degrading the user experience. We avoid this with the asynchronous fire and forget pattern shown here. The server splits the output into two simultaneous paths: a 302 response that arrows back to the user in under 5 milliseconds, and a click event that drops into a Kafka queue. The application server considers its job done the moment the event hits Kafka. The user's redirect speed is now completely decoupled from the analytics processing time. Downstream, the analytics pipeline takes over. A stream processor like Flink consumes the Kafka events, aggregates them, and inserts them into an OLAP database like ClickHouse to update live performance charts. This follows the golden rule of scale: never allow a secondary operational requirement like analytics to block a Tier 0 critical path like redirection. Bringing these components together reveals the complete global architecture, separated into 3 distinct zones. The write path solves the collision problem using distributed counters and Base62 encoding. The read path embraces the 302 redirect for data visibility while protecting the database through layered caches and request coalescing. And the analytics path ensures sub-10 millisecond speeds by offloading data ingestion to an asynchronous message queue. This isolated architecture perfectly absorbs the 100-to-1 scale asymmetry that crushes standard web applications. System design at this scale isn't about finding a magic database. Instead, it is about strict architectural restraint, knowing exactly what execution paths must be kept completely clear of heavy system-crushing operations. By respecting these boundaries, we guarantee that a viral link resolves in milliseconds every single time.